Hello, welcome back. Let's start reading. The weather's very nice. So I'd like to read about this jet engines. I'm sorry for the noise, my computer, because this blower, the air blower, electric air blower is damaged. So it makes noise, but I'm like old air condition. Sound like an old damaged air condition. But I don't have the money to replace my computer yet.
Jet engine. A jet engine is a type of reaction engine, discharging a fast-moving jet of heated gas, usually air, that generates thrust by jet propulsion. While this broad definition may include rocket, water jet, and hybrid propulsion, the term jet engine typically refers to an internal combustion air-breathing jet engine such as a turbojet, turbofan, ramjet, pulse jet, or scramjet. In general, jet engines are internal combustion engines. Air-breathing jet engines typically feature a rotating air compressor powered by a turbine, with the leftover power providing thrust through the propelling nozzle. This process is known as the Brayton thermodynamic cycle. Jet aircraft use such engines for long-distance travel. Early jet aircraft used turbojet engines that were relatively inefficient for subsonic flight. Most modern subsonic jet aircraft use more complex high-bypass turbofan engines. They give higher speed and greater fuel efficiency than piston and propeller aero engines over long distances. A few air-breathing engines made for high-speed applications, ramjets and scramjets, use the ram effect of the vehicle's speed instead of a mechanical compressor. The thrust of a typical jetliner engine went from 5,000 lbf, 22 kN, de Havilland Ghost turbojet, in the 1950s to 115,000 lbf, 510 kN, General Electric GE90 turbofan, in the 1990s, and their reliability went from 40 in-flight shutdowns per 100,000 engine flight hours to less than 1 per 100,000 in the late 1990s. This, combined with greatly decreased fuel consumption, permitted routine transatlantic flight by twin-engined airliners by the turn of the century, where previously a similar journey would have required multiple fuel stops. History, edit. Main article, History of the jet engine. See also, Timeline of jet power. The principle of the jet engine is not new, however, the technical advances necessary to make the idea work did not come to fruition until the 20th century. A rudimentary demonstration of jet power dates back to the Aeolipile, a device described by Hero of Alexandria in 1st century Egypt. This device directed steam power through two nozzles to cause a sphere to spin rapidly on its axis. It was seen as a curiosity. Meanwhile, practical applications of the turbine can be seen in the water wheel and the windmill. Historians have further traced the theoretical origin of the principles of jet engines to traditional Chinese firework and rocket propulsion systems. Such devices' use for flight is documented in the story of Ottoman soldier Lagari Hassan Celebi, who reportedly achieved flight using a cone-shaped rocket in 1633. The earliest attempts at air-breathing jet engines were hybrid designs in which an external power source first compressed air, which was then mixed with fuel and burned for jet thrust. The Italian Caproni Campini N.1 and the Japanese Zu-11 engine intended to power Oka kamikaze planes towards the end of World War II were unsuccessful. Even before the start of World War II, engineers were beginning to realize that engines driving propellers were approaching limits due to issues related to propeller efficiency, which declined as blade tips approached the speed of sound. If aircraft performance were to increase beyond such a barrier, a different propulsion mechanism was necessary. This was the motivation behind the development of the gas turbine engine, the most common form of jet engine. The key to a practical jet engine was the gas turbine, extracting power from the engine itself to drive the compressor. The gas turbine was not a new idea. The patent for a stationary turbine was granted to John Barber in England in 1791. The first gas turbine to successfully run self-sustaining was built in 1903 by Norwegian engineer Egidius Selling. Such engines did not reach manufacture due to issues of safety, reliability, weight and, especially, sustained operation. The first patent for using a gas turbine to power an aircraft was filed in 1921 by Maxime Guillaume. His engine was an axial flow turbojet, but was never constructed, as it would have required considerable advances over the state-of-the-art in compressors. Alan Arnold Griffith published an aerodynamic theory of turbine design in 1926, leading to experimental work at the RAE. In 1928, RAF College Cranwell cadet Frank Whittle formally submitted his ideas for a turbojet to his superiors. In October 1929, he developed his ideas further. On the 16th of January 1930, in England, Whittle submitted his first patent, granted in 1932. The patent showed a two-stage axial compressor feeding a single-sided centrifugal compressor. Practical axial compressors were made possible by ideas from A. Griffith in a seminal paper in 1926, An Aerodynamic Theory of Turbine Design. Whittle would later concentrate on the simpler centrifugal compressor only. Whittle was unable to interest the government in his invention, and development continued at a slow pace. Heinkel He-178, the world's first aircraft to fly purely on turbojet power. In Spain, pilot and engineer Virgilio Loret Ruiz was granted a patent for a jet engine design in March 1935. Republican President Manuel Aznar arranged for initial construction at the Hispano-Suiza aircraft factory in Madrid in 1936, but Loret was executed months later by Francoist Moroccan troops after unsuccessfully defending his seaplane base on the first days of the Spanish Civil War. His plans, hidden from Francoists, were secretly given to the British Embassy in Madrid a few years later by his wife, Carlota O'Neill, upon her release from prison. In 1935, Hans von Hahn started work on a similar design to Whittle's in Germany, both compressor and turbine being radial, on opposite sides of the same disc, initially unaware of Whittle's work. Von Hahn's first device was strictly experimental and could run only under external power, but he was able to demonstrate the basic concept. A Hahn was then introduced to Ernst Heinkel, one of the larger aircraft industrialists of the day, who immediately saw the promise of the design. Heinkel had recently purchased the Herth Engine Company, and a Hahn and his master machinist Max Hahn were set up there as a new division of the Herth Company. They had their first Hees-1 centrifugal engine running by September 1937. Unlike Whittle's design, a Hahn used hydrogen as fuel, supplied under external pressure. Their subsequent designs culminated in the gasoline-fueled Hees 3 of 5 kN, 1100 lbf, which was fitted to Heinkel's simple and compact He-178 airframe and flown by Erich Warsitz in the early morning of the 27th of August, 1939, from Rostock Mariani Aerodrome. an impressively short time for development. The He-178 was the world's first jet plane. Heinkel applied for a U.S. patent covering the aircraft power plant by Hans Joachim Pabst von Erhaen on the 31st of May, 1939, patent number US 2256198, with M. Hahn referenced as inventor. Von Erhaen's design, an axial flow engine, as opposed to Whittle's centrifugal flow engine, was eventually adopted by most manufacturers by the 1950s. Austrian Anselm Franz of Junkers engine division, Junkers Motor or Jumo, introduced the axial flow compressor in their jet engine. Jumo was assigned the next engine number in the RLM 109-0XX numbering sequence for gas turbine aircraft power plants, 004, and the result was the Jumo 004 engine. After many lesser technical difficulties were solved, mass production of this engine started in 1944 as a power plant for the world's first jet fighter aircraft, the Messerschmitt Me 262, and later the world's first jet bomber aircraft, the Aradu R-234. A variety of reasons conspired to delay the engine's availability, causing the fighter to arrive too late to improve Germany's position in World War II. However, this was the first jet engine to be used in service. Gloucester Meteor F.3s. The Gloucester Meteor was the first British jet fighter and the Allies' only jet aircraft to achieve combat operations during World War II. Meanwhile, in Britain the Gloucester E-28/39 had its maiden flight on the 15th of May, 1941 and the Gloucester Meteor finally entered service with the RAF in July, 1944. These were powered by turbojet engines from Power Jets Limited, set up by Frank Whittle. The first two operational turbojet aircraft, the Messerschmitt Me 262 and then the Gloucester Meteor entered service within 3 months of each other in 1944, the Me 262 in April and the Gloucester Meteor in July. The Meteor only saw around 15 aircraft enter World War II action, while up to 1,400 Me 262 were produced, with 300 entering combat, delivering the first ground attacks and air combat victories of jet planes. Following the end of the war, the German jet aircraft and jet engines were extensively studied by the victorious Allies and contributed to work on early Soviet and US jet fighters. The legacy of the axial flow engine is seen in the fact that practically all jet engines on fixed-wing aircraft have had some inspiration from this design. By the 1950s, the jet engine was almost universal in combat aircraft, with the exception of cargo, liaison and other specialty types. By this point, some of the British designs were already cleared for civilian use, and had appeared on early models like the de Havilland Comet and Avro Canada jetliner. By the 1960s, all large civilian aircraft were also jet-powered, leaving the piston engine in low-cost niche roles such as cargo flights. The efficiency of turbojet engines was still rather worse than piston engines, but by the 1970s, with the advent of high-bypass turbofan jet engines, an innovation not foreseen by the early commentators such as Edgar Buckingham, at high speeds and high altitudes that seemed absurd to them, fuel efficiency was about the same as the best piston and propeller engines. Uses, edit. Jet engines power jet aircraft, cruise missiles and unmanned aerial vehicles. In the form of rocket engines they power model rocketry, spaceflight, and military missiles. Jet engines have propelled high-speed cars, particularly drag racers, with the all-time record held by a rocket car. A turbofan-powered car, Thrust SSC, currently holds the land speed record. Jet engine designs are frequently modified for non-aircraft applications, as industrial gas turbines or marine power plants. These are used in electrical power generation, for powering water, natural gas, or oil pumps, and providing propulsion for ships and locomotives. Industrial gas turbines can create up to 50,000 shaft horsepower. Many of these engines are derived from older military turbojets such as the Pratt & Whitney J57 and J75 models. There is also a derivative of the P&W JT8D low bypass turbofan that creates up to 35,000 horsepower, HP. Jet engines are also sometimes developed into, or share certain components such as engine cores, with turboshaft and turboprop engines, which are forms of gas turbine engines that are typically used to power helicopters and some propeller-driven aircraft. Types of jet engine, edit. There are a large number of different types of jet engines, all of which achieve forward thrust from the principle of jet propulsion. Air breathing, edit. Main article, air breathing jet engine. Commonly aircraft are propelled by air breathing jet engines. Most air breathing jet engines that are in use are turbofan jet engines, which give good efficiency at speeds just below the speed of sound. Turbojet, edit. Main article, turbojet. A turbojet engine is a gas turbine engine that works by compressing air with an inlet and a compressor, axial, centrifugal, or both, mixing fuel with the compressed air, burning the mixture in the combustor, and then passing the hot, high-pressure air through a turbine and a nozzle. The compressor is powered by the turbine, which extracts energy from the expanding gas passing through it. The engine converts internal energy in the fuel to increased momentum of the gas flowing through the engine, producing thrust. All the air entering the compressor is passed through the combustor and turbine, unlike the turbofan engine described below. Turbofan, edit. Main article, turbofan. Turbofans differ from turbojets in that they have an additional fan at the front of the engine, which accelerates air in a duct bypassing the core gas turbine engine. Turbofans are the dominant engine type for medium and long-range airliners. Turbofans are usually more efficient than turbojets at subsonic speeds, but at high speeds their large frontal area generates more drag. Therefore, in supersonic flight, and in military and other aircraft where other considerations have a higher priority than fuel efficiency, fans tend to be smaller or absent. Because of these distinctions, turbofan engine designs are often categorized as low bypass or high bypass, depending upon the amount of air which bypasses the core of the engine. Low bypass turbofans have a bypass ratio of around 2:1 or less. Advanced Technology Engine, edit. Main article, Advanced Technology Engine. The term Advanced Technology Engine refers to the modern generation of jet engines. The principle is that a turbine engine will function more efficiently if the various sets of turbines can revolve at their individual optimum speeds, instead of at the same speed. The true advanced technology engine has a triple spool, meaning that instead of having a single drive shaft, there are three, in order that the three sets of blades may revolve at different speeds. An interim state is a twin-spool engine, allowing only two different speeds for the turbines. Ram compression, edit. Further information, ramjet and scramjet. Ram compression jet engines are air-breathing engines similar to gas turbine engines insofar as they both use the Brayton cycle. Gas turbine and ram compression engines differ, however, in how they compress the incoming airflow. Whereas gas turbine engines use axial or centrifugal compressors to compress incoming air, ram engines rely only on air compressed in the inlet or diffuser. A ram engine thus requires a substantial initial forward airspeed before it can function. Ramjets are considered the simplest type of air-breathing jet engine because they have no moving parts in the engine proper, only in the accessories. Scramjets differ mainly in the fact that the air does not slow to subsonic speeds. Rather, they use supersonic combustion. They are efficient at even higher speed. Very few have been built or flown. Non-continuous combustion, edit. Type description advantages disadvantages. Motorjet works like a turbojet but a piston engine drives the compressor instead of a turbine. Higher exhaust velocity than a propeller, offering better thrust at high speed. Heavy, inefficient and underpowered. Example, Caproni Campini N.1. Pulse J air is compressed and combusted intermittently instead of continuously. Some designs use valves. Very simple design, used for the V-1 flying bomb and more recently on model aircraft. Noisy, inefficient, low compression ratio, works poorly on a large scale, valves on valve designs wear out quickly. Pulse detonation engine similar to a pulse J, but combustion occurs as a detonation instead of a deflagration, may or may not need valves. Maximum theoretical engine efficiency. Extremely noisy, parts subject to extreme mechanical fatigue, hard to start. Detonation, not practical for current use. Other types of jet propulsion, edit. Rocket, edit. Main article, rocket engine. The rocket engine uses the same basic physical principles of thrust as a form of reaction engine, but is distinct from the jet engine in that it does not require atmospheric air to provide oxygen. The rocket carries all components of the reaction mass. However, some definitions treat it as a form of jet propulsion. Because rockets do not breathe air, this allows them to operate at arbitrary altitudes and in space. This type of engine is used for launching satellites, space exploration and crewed access, and permitted landing on the Moon in 1969. Rocket engines are used for high-altitude flights, or anywhere where very high accelerations are needed, since rocket engines themselves have a very high thrust-to-weight ratio. However, the high exhaust speed and the heavier, oxidizor-rich propellant results in far more propellant use than turbofans. Even so, at extremely high speeds they become energy efficient. An approximate equation for the net thrust of a rocket engine is F sub n equals m dot above G sub 0 of I sub sp comma vac minus a sub e times p, where F sub n is the net thrust, I sub sp comma vac is the specific impulse, G sub 0 is a standard gravity, m dot above is the propellant flow in kg/s, a sub e is the cross-sectional area at the exit of the exhaust nozzle, and p is the atmospheric pressure. Type description advantages disadvantages. Rocket carries all propellants and oxidants on board, emits jet for propulsion, very few moving parts. Mach 0 to Mach 25 plus, efficient at very high speed, Mach 5.0 or so. Thrust forward/weight ratio over 100. No complex air inlet. High compression ratio. Very high speed, hypersonic, exhaust. Good cost forward/thrust ratio. Fairly easy to test. Works in a vacuum, indeed, works best outside the atmosphere, which is kinda on vehicle structure at high speed. Fairly small surface area to keep cool, and no turbine in hot exhaust stream. Very high temperature combustion and high expansion ratio nozzle gives very high efficiency, at very high speeds. Needs lots of propellant. Very low specific impulse, typically 100 for 50 seconds. Extreme thermal stresses of combustion chamber can make reuse harder. Typically requires carrying oxidizor on board, which increases risks. Extraordinarily noisy. Hybrid, edit. Combined cycle engines simultaneously use two or more different principles of jet propulsion. Type description advantages disadvantages. Turborocket, a turbojet where an additional oxidizer such as oxygen is added to the airstream to increase maximum altitude very close to existing designs, operates in very high altitude, wide range of altitude and airspeed limited to same range as turbojet engine. Carrying oxidizer like LOX can be dangerous. Much heavier than simple rockets. Air-augmented rocket, essentially a ramjet where intake air is compressed and burnt with the exhaust from a rocket Mach 0 to Mach 4.5+, can also run exoatmospheric. Good efficiency at Mach 2 to 4, similar efficiency to rockets at low speed or exoatmospheric. Inlet difficulties, a relatively undeveloped and unexplored type. Cooling difficulties, very noisy. Thrust forward/weight ratio is similar to ramjets. Pre-cooled jets forward/lace intake air is chilled to very low temperatures at inlet in a heat exchanger before passing through a ramjet and forward/or turbojet and forward/or rocket engine. Easily tested on ground. Very high thrust forward/weight ratios are possible, 14. Together with good fuel efficiency over a wide range of airspeeds, Mach 0 5.5+. This combination of efficiencies may permit launching to orbit, single stage, or very rapid, very long distance intercontinental travel. Exists only at the lab prototyping stage. Examples include RB545, reaction engine Sabre, Atrex. Requires liquid hydrogen fuel which has very low density and requires heavily insulated tankage. Waterjet, edit. Main article, pump jet. A waterjet, or pump jet, is a marine propulsion system that uses a jet of water. The mechanical arrangement may be a ducted propeller with nozzle, or a centrifugal compressor and nozzle. The pump jet must be driven by a separate engine such as a diesel or gas turbine. Type description: advantages, disadvantages. Water jet for propelling water rockets and jet boats. Squirts water out the back through a nozzle in boats. Can run in shallow water. High acceleration. No risk of engine overload, unlike propellers. Less noise and vibration. Highly maneuverable at all boat speeds. High speed efficiency, less vulnerable to damage from debris, very reliable, more load flexibility, less harmful to wildlife, can be less efficient than a propeller at low speed, more expensive, higher weight in boat due to entrained. Water will not perform well if boat is heavier than the jet is sized for. General physical principles, edit. All jet engines are reaction engines that generate thrust by emitting a jet of fluid rearwards at relatively high speed. The forces on the inside of the engine needed to create this jet give a strong thrust on the engine which pushes the craft forwards. Jet engines make their jet from propellant stored in tanks that are attached to the engine, as in a rocket, as well as in duct engines, those commonly used on aircraft, by ingesting an external fluid, very typically air, and expelling it at higher speed. Propelling nozzle, edit. Main article, propelling nozzle. A propelling nozzle produces a high-velocity exhaust jet. Propelling nozzles turn internal and pressure energy into high-velocity kinetic energy. The total pressure and temperature don't change through the nozzle, but their static values drop as the gas speeds up. The velocity of the air entering the nozzle is low, about Mach 0.4, a prerequisite for minimizing pressure losses in the duct leading to the nozzle. The temperature entering the nozzle may be as low as sea level ambient for a fan nozzle in the cold air at cruise altitudes. It may be as high as the 1000 Kelvin exhaust gas temperature for a supersonic afterburning engine or 2200 K with afterburner lit. The pressure entering the nozzle may vary from 1.5 times the pressure outside the nozzle, for a single-stage fan, to 30 times for the fastest manned aircraft at Mach 3+. Convergent nozzles are only able to accelerate the gas up to local sonic, Mach 1, conditions. To reach high flight speeds, even greater exhaust velocities are required, and so a convergent-divergent nozzle is needed on high-speed aircraft. The engine thrust is highest if the static pressure of the gas reaches the ambient value as it leaves the nozzle. This only happens if the nozzle exit area is the correct value for the nozzle pressure ratio, NPR. Since the NPR changes with engine thrust setting and flight